Hello, my name is Henry McKinnon. I'm here to present to you my Lab 2 motion of a falling object for Physics 2211. Well, first off, the purpose of this lab is to analyze the difference between a freefall and the real world versus two computational models of a freefall, one with drag and one without. We are doing this to have a better understanding of motion and the effect of drag. The system is the object that is dropped, and the forces acting on it, like gravity and drag. The surrounding is the environment where the experiment takes place, and the tools that we use, like the camera and the software. A few of the models and fundamental principles we'll be using: Newton's second law, F equals ma, velocity update formula, the position update formula, force of gravity, force of drag, and a few assumptions that we'll be having is that gravity and drag are the only forces acting on system. The object will start with a velocity of 0. It starts at y equals 0, and the tracker markings are the same location on the object. Here is the video that I used. It is a bottle of shampoo that was dropped 1.2 meters above the ground. There is 0.033 seconds between points. There's possible error as some of the tracker might not have been placed perfectly. This is the close script code that I used. As you can see, the ball was 0.23 kilograms. Excuse me, the shampoo was 0.23 kilograms. It started at 0, 0, 0 for velocity and position. Time starts at 0. The delta t was 0.033. Gravity is 9.8. And j hat, the unit vector, is 0, 1, 0 at the start. 0.467 is the length of the glow script, as that is the length of the tracker experiment. For the simulation, that is just gravity. Force of gravity equals negative g times the ball.m times j hat, and f net equals f grav. Then, to find the velocity, you do ball velocity plus f net over ball.m times delta t. That's just basic principles that I went over earlier. The ball position equals ball position plus ball velocity times delta t. For the simulation that had drag and gravity, drag is set at 0.022. That's the B number. And the same time. And ball speed, though, look at the square root of ball velocity squared plus ball velocity y squared plus ball velocity v squared. And force of grav equals a vector of 0, negative g times ball m, 0. Force of drag will be b times ball dot speed squared times j hat. And f net equals f drag plus f drag, and it's the same equations for velocity and position. As you can see from this, the results, there's small deviations in the paths, but it was a pretty small time interval, so that there wasn't that much time for anything big to happen. If there was a longer interval, there would be bigger deviations. But as you can see, they all look pretty similar. Which models predict a terminal velocity? The model of gravity and drag predicts a terminal velocity. As you can see, when ran for longer, it will eventually hit a terminal velocity. F net will equal 0, as F drag will cancel out the F of gravity. Imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? No, as you can see from the graphs on the right, even though they started at different velocities, they still had the same terminal velocity. All right, thank you for watching.